Good afternoon, ladies and gentlemen. My name is Chen. I'm from Taiwan National Cheng University. I'm here to present our paper, Hardware Trojan Design and Detection with Formal Verification to Deep Neural Network. This is our agenda. First, we will give a brief introduction to this work and our target convolutional neural network design for verification. Next, we will talk about our hardware Trojan implementation, their impacts on accuracy, and hardware overhead. Then, we will use formal verification to detect our proposed hardware Trojan and compare with well-known random simulation. Last, we summarize our Trojan design and verification results to make conclusions. In recent years, IPs are widely used, and neural networks become more and more common. For the hardware security issue, some industrial companies use IPs but have concern of that if their confidential data will be leaked out through those IPs. In this work, we introduce two main topics. One is our Trojan design, and they are focused on attacking the data path of the convolutional neural network design, which is for any dataset. The other is how we apply formal verification to identify the Trojan. For our Trojan design, they can be divided into two categories in this work, according to their targets. We can decrease convolutional neural network classification accuracy by changing data paths and leak confidential data, such as well-trained weight and bias, by adding a single illegal path. At the beginning, we bring out the convolutional neural network architecture of our succeeding Trojan design and verification experiment. The left figure shows the layer structure of neural network. The CNN outputs 10 logits for each handwritten digit, and the class with largest digit value is the predict result made by CNN. The right figure is our whole hardware CNN design diagram, and it can be separated into two parts. On the top of design diagram are modules for convolution, and the bottom parts are modules which handle fully connected operation. Although the SRAM modules are included in the design diagram we show here, CNN module does not contain the SRAM in the realistic implementation. According to our testing, the accuracy of this CNN design can achieve 99.64%. As we mentioned in the previous slide, the CNN design can be composed of convolution and fully connected parts. We will first introduce the convolution part in this slide. The SRAM-A module stores the input image data. SRAM-B and SRAM-D stores the internal result from the first and second convolution result, respectively. And SRAM-weight saves the well-trained weight and bias, which may face to the risk of confidential data leakage. Once the two convolution operations are completed, the convolution down signal will be sent to the fully connected module for the following operation. When the convolution is finished, the fully connected module will take the second convolution result from SRAM-D to deal with the multiply accumulate operation. After two fully connected operations are accomplished, the fully connected down signal will be activated, which means the classification task is completed, and the 10 logit results are stored in SRAM-F. In this part, we will start to discuss the hardware Trojan design. Generally, the hardware Trojan design includes two parts: triggering condition design and design the malicious behaviors. We will focus on triggering condition design in this slide. The triggering condition is used to design when the malicious behaviors will be activated. There are two main categories of sequential triggering designs, named real-value trigger and time-related trigger. Combining two triggering strategies to one hybrid triggering design is feasible as well. We use hybrid triggering condition in our Trojan design, and the triggering flow is shown in the following figure. The first triggering condition of our Trojan is real value based, and it will be activated through a specific sequence of input class. The sequence length we use is A inputs. When the real value trigger is activated, it will start a counter inside the hardware CNN for relative time trigger. The counter will count for a specific number of clock cycles before the time-related trigger is activated. Once the condition of time-related trigger is satisfied, the malicious behavior of the hardware Trojan will be launched. Next, we will discuss our two malicious behavior design. The first type of our malicious behavior design is changing input data paths and wait paths of convolution operation, which will lead to the incorrect result. The original data flow of convolution data, such as input pixel value or weight value, its convolution controller will send an address of convolution data to SRAM. And SRAM will output the data according to the address to data register, which is data buffer of convolution. The Trojan here is to replace the convolution data to the address of convolution data. Therefore, the convolution result will be wrong. The second type of our malicious behavior design is adding an illegal path, which will bring the confidential data outside of the CNN module. The original data flow of the convolution weight value should be saved in the data register and sent to the convolution and pooling module to do convolution operation. After the computation, the result will be quantized and become the final convolution result. The Trojan here is to concatenate the weight value read from SRAM with the final convolution result, so the weight data will be leaked out from the convolution module. In this slide, we present the RTL implementation code of the proposed two malicious behavior design. The top RTL code is for the malicious behavior that changing data paths of the convolution. Here, we take changing the weight and bus data paths for example. The RTL implementation will be similar to changing one or multiple input data paths. Data reg module is the data buffer of convolution module. It will store the data for convolution operation. Trigger 2 is the signal of triggering condition, which is FT high. If the triggering condition is satisfied, data reg module will take the address signal, SRAM R address weight, which is used to access weight and bus data from SRAM as its input. Otherwise, the correct weight and bus data, SRAM R data weight, will be chosen. The bottom RTL code is for the malicious behavior that leaking the confidential data. SRAM W data B is the primary output of whole CNN module, and it is used to bring out the data that will be written to SRAM. While the triggering condition is activated, the well-trained weight and bus data will be concatenated with the original output data and be sent to the outside of CNN design. For the concealment, encoding mechanism can be used to keep the number of output bits unchanged in the future work. We test our CNN design with 5,000 random selected images from MNIST dataset, and the classification accuracy of each test case are shown in the table below. As we mentioned before, the CNN without Trojan included has 99.64% classification accuracy. For the Trojan light-changing pixel data path, the accuracy of CNN with one pixel path Trojan embedded only dropped less than 3%, which is due to neural network's ability of error tolerance. However, error tolerance is limited. The decline of accuracy is proportional to the number of data paths that be influenced by the Trojan. Because more pixel paths will change, the proportion of correct data will be decreased. We can also observe that the Trojan changes weight and bias data paths, means using arbitrary value as weight and bias to do classification. So its classification accuracy dropped significantly to around 6%. For the Trojan not leaking confidential data, as we mentioned in page 9, its target is data leakage. So the adding illegal path does not do any modification on calculation function, or alerting the input value of the computation module that will impact classification accuracy. As shown in the table, its accuracy remains the same as Trojan-free design. We run logic synthesis of the module with malicious behavior included under TSMC 90nm process by using Synopsys design compiler. The reason why we estimate the hardware cost of each malicious behavior is the Trojan may be detected by conventional verification tools due to its noticeable hardware costs. We will discuss Trojan detection in this part. First, we use traditional random simulation to detect our proposed Trojan. In our simulation setup, the test bench will randomly select images from MNIST dataset into CNN for classification. And we use internal random function of Verilog for random mechanism. In our experiment, the probability to trigger our real value sequence is 1/10 to the power of 8, which is a very rare corner case for random simulation. As a result, the test bench ran 2 million images for around 7 days and did not trigger the real value triggering condition. Additionally, the 2 million images selected by test bench can be repeated due to the MNIST dataset has only 70,000 images. And this selection strategy will not cause any problem to the simulation test, because we use image class sequence as real value triggering condition, not a specific image. The main purpose we want to present in this slide is that under certain Trojan, such as one pixel path Trojan and data leakage Trojan, the Trojan's impact on classification accuracy is unnoticeable. For those cases that remain over 95% accuracy, it may be difficult to motivate design verification engineers to do exhaustive functional verification, due to its classification accuracy is still acceptable. The other key points of this work is that we use assertion-based formal verification technique to detect our two proposed types of Trojan. Both formal property verification and security path verification methodologies are provided by Cadence AlphaGo, and they are developed based on model tracking, which is a formal verification technique. Both formal property verification and security path verification can detect data path Trojan, but formal property verification is not appropriate for data leakage Trojan. The security path verification app will help us to point out the path specified in SPV assertion. In our verification perspective of data paths, The concept is that we consider the input data that's sent into the computation module should come from SRAM. It can ensure that the input value will get the data that's saved in SRAM. Therefore, we set up a SPV assertion to declare that the data passed from convolution controller's wait address signal to the convolution buffer's input, and it does not pass through SRAM's output is not acceptable. If the path exists, it means that the data received by the operation module may not come from SRAM. We want to describe the data flow of Trojan-free design first, and we take wait data path for example. Before we start, we have to clarify some key elements in this figure. We have non-net module, which represent the whole CNN design, and consists of convolution module, named convolution top. The SRAM R address weight is the source of convolution SRAM R address weight, which is the address signal for accessing SRAM from convolution controller. The convolution SRAM R data weight is the weight or bias of convolution operation, and it will pass through the input of data register, which is SRAM R data weight. In this figure, we show the data accessing path of Trojan-free design. From source, SRAM R address weight goes through SRAM module and ends at the destination, SRAM R data weight. The data flow of input pixel path is similar to this case. Here, we present in this figure is the changing weight path Trojan detected by our SPV assertion. The red color path is the counterexample path. We can observe that the red color path from SRAM R address weight to SRAM R data weight, which does not pass through SRAM. So this path violates our SPV assertion, which means this red path has a high probability to send the wrong data to the destination module. This figure is changing input pixel path Trojan detected by our SPV assertion. Similarly, the SRAM R address B0 and SRAM R data B0 is the address and data of the one pixel path. The red color path is the counterexample path. In this red path, the data flow starts from SRAM R address B0 to SRAM R data B0, does not pass through SRAM. So the destination may receive the incorrect data, which is not from SRAM. For the other replication concern, the concept is that we consider the confidential data must be used in the convolution operation and should not be leaked to the outside of CNN. It can guarantee that the weights or bias are stayed in the convolution module. Therefore, we set up a SPV assertion to identify the path, starting from SRAM and ending at the primary output of CNN, but not pass through the calculation module of convolution. If the path exists, it means that the confidential data are fed to the thread to be stolen out of the CNN design. First, we will use this figure to describe the data flow of Trojan-free design. Before we start, we will also clarify some key elements in this figure. The SRAM R data weight is the weight and bias data, which comes from SRAM weight. And the weight and bias data will be used in multiply, compare, and quantize, which are the two calculation modules of convolution. After apply convolution operation, out will be the convolution result, and it will be written back to SRAM outside CNN module through SRAM W data B. Here, represented in this figure is the data leakage Trojan detected by our SPB assertion. The red color path is the counterexample path. We can observe that the red color path from our data of SRAM weight to SRAM W data B temp, which is the primary output of CNN design, and it does not pass through convolution calculation modules. So there exists an illegal path that brings the computational data out of CNN design directly. Here is the summary of this work. We used the hybrid triggering condition to launch our two hardware Trojans. Basically, our two present hardware Trojans are used to emphasize that we need to guarantee the well-trained data should be correctly used and security protected. Based on our result, formal verification is a flexible methodology that can efficiently and effectively detect the hardware Trojan. Especially, we think that the security path tracking with formal method is crucial to neural network designs. Thank you for listening.